I wish everyone a nice day. Allow me to introduce myself. My name is Miriam Nicolanska and I'm a master's student at the University of Zilina in the Department of Power Engineering. I would first like to thank the head of the Department of Power Engineering, Mr. Michal Holubcik, alongside with the principal of the University of Zilina, Professor Jozef Jandacka, for this opportunity and their kind cooperation. The topic of today's presentation is design of a low-cost wireless emission monitoring system for solid fuel heat sources. This presentation is a part of the 8th European Alliance for Innovation International Conference on Mobility, LOT and Smart Cities, taking place November 24th to 26th in Portugal. The European Alliance for Innovation is a non-for-profit organization that drives innovations and the global research in aims of reaching a sustainable yet powerful future. Generally speaking, air quality regulation can be viewed in 4 important parts. Number 1, emission production, either caused by heating devices such as boilers, fireplaces in households, or for instance by local transport of taxis, buses or cars within the city. Number 2, monitoring and measurements of emission levels. Handheld diagnostic devices used during boiler inspections or continuous monitoring stations. Number 3, air quality regulations, indexes and emission norms. And lastly, possible countermeasures and mitigations that can take place to decrease emissions, reach the regulation levels and ultimately improve air quality within a city. Heating devices within households burn fuel to produce heat. This process, however, releases unwanted pollutants into the air. These are generally divided into 3 groups: PM, particulate matter, PM 2.5 and PM 10. Greenhouse gases such as CO2 and carbon dioxide, CH4, methane, N2O, nitrous oxide, O3, ozone, and other more dangerous compounds. The concentrations are commonly measured in parts per million units or milligrams of the pollutant per cubic meter of air. According to a Slovakian study, the average age of solid fuel boilers in Slovakia is 12 years, and for fireplace stoves up to 21 years. To add to the first fact, over 57% of citizens use outdated heating systems. Neglected maintenance increases fuel waste, some sources showing over 25% heat losses. The European Commission had set the 2030 climate target plan, in which a European target has been set to decrease the greenhouse gas emissions by at least 55% below the level from the year 1990. Air quality can be objectified through emissions or emissions. The difference is, however, important. Emissions relate to the amount of particles emitted from a specific heat source, generally measured in the chimney. Emissions, on the other hand, relate to the amount of polluting substances present within the environment and air within the surroundings. Emission norms orientate to protect human health and the environment too. Measurement of emission levels can be done directly within the chimney using a portable diagnostic devices. Measurement of emissions are done using automatic monitoring stations. In Slovakia, there are 50 active monitoring stations over districts to date. The World Health Organization and the European Union state maximum levels of substances within the air. Firstly, take note the differences in the measurement durations, which can be hourly, daily, yearly, or even smaller. For instance, concentrations of dust are measured in days or years, whereas nitrous oxide is measured only as an hourly average. To counter this, the new European Union regulation number 2015/1189 endorses the Eco Design Directive. The directive defines minimum mandatory requirements regarding to emission and energy efficiencies of boilers, and classifies boilers into 5 distinct classes. Class 1 up to Class 5, based on emission and efficiency measurements. From the beginning of 2022, for instance, the operation and production of boilers of emission class 1 or 2 shall be legally banned. From 2030, it is considered that all 3 lowest classes will be banned from use. These boilers must be identified and replaced till then. The first study demonstrated the use of a wireless sensor network in the early detection of forest fires. The system nodes were placed throughout a remote forest and divided the areas based on predicted fire risk: high active, medium active, and low active. This allows to prioritize the areas that need to be inspected more frequently. The second study remotely monitored a landslide-prone zone within a hilly mountain demographic. The goal was to predict landslide activity. The sensors send the signals through a wireless network into a global database or application on a computer. The picture in the bottom right corner illustrates the position of the sensors on the mountains. This brings me to the requirements of the emissions monitoring device. A couple of design requirements will drive the engineering process. First, the system must be placed within the chimney or exhaust of the heating device. Thus, the structure shall withstand this hostile environment and protect from temperatures and particles reaching up to 200, sometimes 25 degrees Celsius. Second, the system must measure emission levels and send the data accurately to the database without the use of Wi-Fi. Rather, an independent data transmission. Third, the device must be easily retrievable for maintenance. Lastly, and arguably most important, the device must be significantly inexpensive than modern equivalents. The air quality monitoring device is placed on the top of a chimney and measures the concentration of emissions from the flue gases and sends this data to the user application. As you can see, the sensor can be placed in both circular and square-shaped chimneys. The external components of the system is a 3D printed thermoresistant skeleton or casing, protection from heat, an emission probe that cools the gas down, and energy harvesting or solar panels. It is very likely that active cooling system or ventilators shall be used in a casing. The key systems are 1 and 2 are energy system, such as Li-ion battery pack with solar panels. Number 3, transmission system, 2G or 3G SIM card transmission model, the Arduino-based GPRS GSM Shield SIM 900. Number 4, system controller or a mini computer, the Arduino Uno unit. Number 5 is antenna. Number 6 is micro SD. And number 7, emission and temperature sensors. The sensors can measure the emission concentrations such as carbon dioxide, methane, and dust concentrations, PM2.5 and PM10. The Arduino then sends the data to a user application where users such as myself or any government employee or regulating party can view in real time. Use this data to improve air quality. The application presents the data using a color map. Green, yellow indicating favorable emission levels. Red and brown indicates less favorable conditions, and finally black areas in which emission levels are dangerously high. This allows the user to take actions in areas that matter within the smart city. One possible mitigation is to increase inspections for the households, inspect the smoke color, etc. Two numerical models will be built in the future, a telecommunication model within MATLAB and a thermal finite element method model within ANSYS Fluent. The first model will allow to design the Arduino signaling, the antenna, the power needed to the data from the transmitted through various signal losses and into the receiver. It will also allow to evaluate conditions such as maximum distance of a sensor from the main node or calculate parameters such as signal-to-noise ratio. The second model will focus on the thermal aspects. It is important to ensure that the air cools to a room temperature before entering the device. Otherwise, the 200 degrees Celsius gases will permanently damage the sensors. This model will calculate parameters such as the airflow rate within the device, the condensation of the gas, or the temperature distribution within the skeleton. Just to emphasize, the temperature from within the casing must not exceed temperatures of 30 Celsius. The future design stages will consist of building prototypes alongside numerical models. The first two prototypes will be built to verify the functionality of the concept in a normal, non-hostile environment. The prototype consists of 5 sensors: the MQ131 ozone sensor, the MP503 VOC sensor, the popular particulate matter sensor PMS5003, MHZ19 CO2 sensor, and the DHT22 temperature and humidity sensor. The Arduino processes this data and displays it on an interactive touchscreen. The only difference is in a probe and heat resistant structure. After this is done, the first sensor within the exhaust will be made. Here, a special attention must be kept around the air sampling and electronics cooling. It is very likely that the active cooling will be needed to cool the inside electronics. This test will only consist of sampling the flue gases and saving the data via Wi-Fi connection. The second test will send the data via 2G SIM card model, testing the required power and signal strength to find through the weather conditions and distance. Allow me to summarize the presentation. The design presents an inexpensive solution to monitoring real-time emissions. It increases the amount and accuracy of air quality data and allows government officials and citizens like you and me to view that locations in a smart city need our help. Thank you for your attention.